In Chapter 9, we'll focus on the structures and reactions of alcohols, ethers, and epoxides. To start out with, 9.1 is the intro. Why are all three of these functional groups together in one chapter? And the reason is because they all contain carbon-oxygen sigma bonds. That's going to make some of their reactivity similar. So let's start with alcohols. Alcohols have an OH group on them. So the generic way to write it would be like ROH, so R is just some alkyl group. The OH is bonded to an sp3 carbon. It's important that it's sp3. If it's sp2, that makes it a different functional group actually. We'll talk about those in a couple chapters. We can have primary alcohols, where there are two hydrogens on the carbon with the OH. That's the example I showed above, is a primary alcohol. You can have a secondary alcohol where there's one hydrogen on the carbon with the OH. This would be a secondary alcohol. So there's one hydrogen here. And you can have a tertiary alcohol. There's zero hydrogens on the carbon with the OH. And that would be a tertiary alcohol. Next we can have ethers. And ethers have two alkyl groups bonded to oxygen. So for example, that's diethyl ether. So here's our oxygen. On one side there's a carbon group, on the other side there's a carbon group. And we can have symmetrical ethers, where both alkyl groups are the same. And we can have unsymmetrical ethers, where the alkyl groups are different. So for that you could have something like methyl on one side and ethyl on the other, ethyl-methyl ether. And then we have epoxides. And epoxides contain an oxygen atom in a three-membered ring with two other carbons. So in a way, if you think about it, it's sort of a special class or special group of ether, because ethers have carbons on both sides. So does an epoxide. So an epoxide looks like this, and you can keep going and have other carbons going like that. So it's a three-membered ring with carbons on either end. And the reason that it gets its own group is that it's got different reactivity than a normal ether does. So that's why it's considered its own functional group. So the oxygen atom in all of these functional groups is going to be a sp3 hybrid orbitals. And all of them have two bonds to oxygen and two lone pairs. And the bond angles are all roughly 109.5 degrees. Now that's not exactly true. Some of them are 105 or 107, but for my class I'm going to focus on them being 109.5 because that's pretty close to what the bond angles are going to be, except epoxides. Epoxides must have bond angles of 60 degrees, or roughly 60, because all of the bonds inside of an epoxide have to add up to 180 degrees total for all three of them, because it's inside a triangle. So this actually yields a large degree of angle strain in epoxides. And that's going to make them much more reactive than normal ethers. And of course, all of the CO and all of the OH bonds are highly polarized. with a delta minus on oxygen, delta plus on carbon, delta minus on oxygen, delta plus on hydrogen. And this is what's going to lead to the reactivity of each of these groups. So I'll talk briefly about naming, but most of this I would just read in the textbook because there's not that much that I can add to it. It's just mostly following a bunch of rules. But I'll give you just a little bit. For alcohols, the main rule is to again find the longest chain like we did with alkanes. Except now that we want to find the longest chain that contains the OH. And then we'll name it as before. I'll add all to the end of the name. And we'll number the chain to give the alcohol group the lowest possible number. So an example might be something like this. There are 1, 2, 3, 4 carbons, so that would be named from butane. We drop the E and add all, so now it's butanol. Then we have to figure out where the alcohol group is. 1, 2, 3, 4. So if I number it that way, it would be 2. If I number it the opposite way, it would be 1, 2, 3, 4. So we give the lowest number, so it's 2-butanol. If you have to choose between an alcohol group and an alkyl group, the alcohol group gets the lowest number. So this would be 3-methyl 2-butanol. If we have 2 alcohols on the same molecule, then we name it as a diol. So there are 3 carbons here, so and our groups are at 1, 2, 3, 1, 3, propane diol. If we have ethers, for simple ethers, we just name each side. So name the alkyl group on each side of oxygen, followed by ether. If I look at this one, on one side I've got an ethyl group, on the other side I have a propyl group, and so it just follows the same rules that we've used before, and that is that we put things in alphabetical order. So this would just be ethyl, propyl, ether. For naming an ether as a part of a larger molecule, I can take my ether group, so say it's a CH3O that's attached to something, that would be called methoxy. We can do the same thing with larger ones. If I have 3 carbons and an oxygen attached to something, that would be propoxy. So if I have a larger molecule, I can name this as 1, 2, 3, 4, 5, 6. That's a hexane. And at the 1, 2, 3 position, there's a methoxy. So the name of this compound would be 3-methoxy hexane.